any Bulmash?
Let's see. All right, thank you. Let's see. All right, can you see my screen?
Yep.
Great. Okay. So thank you very much to the organizers for this excellent conference and for inviting me to speak here. So today I'm going to be talking about anomalies in 2+1 dimensional fermionic topological phases. So this is work that I've done at University of Maryland with Sri Tata, Ryohei Kobayashi, and Mason Barkeshley. So let me just start by giving a quick big picture summary of what we've done. So in general, symmetry-enriched 2+1 dimensional fermionic topological phases can be anomalous. That is, they are required to live at the surface of a symmetry-protected topological phase in 3 dimensions, 3 spatial dimensions. And so given a general fermionic SET, we construct a path integral for a fermionic SPT that hosts this SET at its surface, which can be used to compute the anomaly. So let me now go into that in a little more detail. So in general, in topological order, we know that if you add a global symmetry group G, the anions can carry fractional quantum numbers of that symmetry. And in this case, we have a symmetry-enriched topological phase. The best known example of this is probably the fractional quantum Hall effect, where Laughlin anions carry a fractional quantum number under U1 charge conservation. And in general, you may also have a situation where, for example, t squared equals -1 on an anion for time reversal. That is, anions carry a local Kramers degeneracy. And there are a number of examples of this that are known at this point. And the mathematical formalism for describing symmetry fractionalization is, at least in bosonic topological phases, is well developed at this point. Now, symmetry-enriched topological phases can have a 't Hooft anomaly. And what this means is that we cannot preserve gauge invariance when coupling to a G gauge field. And this means that the symmetry cannot be realized in an on-site fashion in a 2+1D system. So I'm exclusively discussing 2+1 dimensional topological orders here. So the workaround for this is to realize the SET on the surface of a 3+1 dimensional G symmetry protected topological phase. So the bulk has no topological order, but the surface does allow a symmetry preserving anomalous SET. So there's a key question here in general, which is if I hand you a particular SET, what 3+1 dimensional SPT hosts the SET at its surface? That is, what is the anomaly? It may be that the SPT is trivial, in which case the SET is allowed to exist in 2+1 dimensions on its own, in which case there is no anomaly. But if the SPT is non-trivial, then there is a non-trivial anomaly. So that's the basic question in symmetry-enriched topological phases, and there has been a lot of progress on answering this question, particularly in bosonic 2+1D SETs. So at this point, the problem is basically solved for bosonic 2+1D SETs. The symmetry fractionalization formalism is well understood. We know how to determine the fractional quantum numbers that anions can carry under global symmetries. And the anomaly is given by part of the SPT data, which is the cohomology class. So it's an H⁴. It's valued in the 4th cohomology group of G with U1 coefficients, where G is the global symmetry group. The relative anomaly has an explicit formula from SET data, and that was given by Meng and Mason. And then in some prior work, Mason and I gave a construction which allows us to compute the absolute anomaly. So from the SET data, we can construct a path integral and use that for the SPT that hosts the SET and use it to compute a complete set of anomaly indicators. At least compute a complete set of anomaly indicators in a large number of cases. Now in fermionic 2+1D SETs, the problem is much more open. The symmetry fractionalization formalism has not been previously fully understood, especially if the symmetry group does not is not just a direct product of fermion parity, which I'm going to refer to as Z2F, with some other symmetry group, which we call the bosonic symmetry group, GB. So an example of this is when time reversal squares to fermion parity, which is familiar from topological insulators in the non-interacting fermion case. There's also a much richer SPT classification involving quite a few different cohomology groups. And in general, the Wang-Gu equations are usually what are used to describe this. And only some special cases of the anomalies have been known. So the problem that we're solving is the following. So given any fermionic 2+1 dimensional topological order, and a generic fermionic symmetry group, so it doesn't have to be a direct product of fermion parity with a bosonic symmetry group of this form. That's not, we're allowing a generic fermionic symmetry group. And symmetry fractionalization data for that fermionic topological order, we're going to produce a path integral model of a fermionic SPT, which hosts the SET on its surface. And if you compute this path integral on various manifolds, you can use that to extract which fermion SPT we have. So that's the basic problem that we're solving. We want to determine what SPT hosts the SET, so we're just going to construct one, given the SET data. The basic idea of our construction is using a notion of fermion condensation, which has been discussed by a number of people here, which I'll get to in a moment. But the idea is that we're going to start with a purely bosonic model, which is going to be a symmetry-enriched Crane-Yetter model, and I'll describe this in a moment. And then this model is going to be a 3+1D model, which has a topologically non-trivial emergent fermion in its bulk. We're then going to use the fermion condensation procedure to condense that fermion. So we're going to turn that fermion into a local excitation. And what will come out at the end is a fermionic SPT with surface fermionic topological order. So let me now discuss these pieces discuss each of these pieces. So the Crane-Yetter model is I didn't actually put a citation on here, but it's well known by Crane and Yetter. And the input to this model is a 2+1 dimensional topological order. Mathematically, it's a braided tensor category, which I'm going to call C. Now, the output of this object, of this construction, if C is modular, which is to say it describes a bosonic topological order, is going to get this construction gives us a trivial 3+1 dimensional bulk and bosonic topological order on the surface, which is given by the input, braided tensor category C. Now, one might hope that you could just input the fermionic topological order into this construction and get out some theory that has fermionic topological order living on its surface. However, that's not the case because the theory is intrinsically bosonic. And so if we input the mathematical data describing a fermionic topological order into this bosonic model, that is, if C is what's called a supermodular braided tensor category, what we get out is a path integral for 3+1 dimensional Z2 gauge theory in the bulk with an emergent bulk fermion and some gapped boundary of that Z2 gauge theory. And you can consider more general inputs to this, the Crane-Yetter model, but that's not going to be interesting for our purposes today. So despite the fact that the Crane-Yetter model can't directly create a fermionic topological order on its surface and with a trivial bulk, we're actually going to use the supermodular case as an input to our theory, and we're going to dress it up so that we get the desired output. So what we're going to start with is a bosonic theory, which is a fermion and symmetry-enriched Crane-Yetter model. So the input to this theory is going to be a fermionic topological order, or a supermodular braided tensor category, and a fermionic symmetry group. And then we're going to add in symmetry fractionalization data for the fermionic symmetry group and a three-form Z2 gauge field F. And what this fermionic gauge field is going to do is insert Wilson lines of the emergent fermion of the Cranial theory. And this is basically a minimal coupling of this three-form Z2 gauge theory to this model. And we're also going to have a background gauge field for the bosonic symmetry group, which is the full fermionic symmetry group, quotient quotient fermion parity. And the output of this model is going to be a path integral for a GB enriched Z2 gauge theory in 3 dimensions. And it's going to have Wilson lines of the emergent fermion. So this is the Z2 charge, which is in this Z2 gauge theory, inserted according to this three-form gauge field F. And of course, the value of this path integral is going to depend on some space-time manifold M. This is actually a generalization of what we used in the bosonic case to compute anomalies in some of our previous work. And in that case, we could just stop here. This was enough to give us a bosonic SPT, but when we're inserting a fermionic topological order, we get something topologically ordered in the bulk instead. So of just a very brief overview of what the construction involves, we have to, for a triangulated manifold, we have to associate a bunch of data to a bunch of the different simplices, some anions to 2 and 3 simplices that obey certain constraints, some symmetry domain walls to 1 simplices, fermion lines to 3 simplices, and an amplitude to each 4 simplex, which is given by a diagram using the modular tensor category graphical calculus, which I don't have any time to go over in the moment at the moment. And then the path integral is just a sum over all of the anion assignments. Now, and I just want to emphasize that these fermion lines, which is the background which is the three-form gauge field, is not being summed over in the bosonic shadow. Now, fermion condensation, which was developed by Guyotto-Kapustin and Asen, Lake, and Walker, is a procedure to take a bosonic theory with an emergent fermion, which I'm going to call psi, such as the one I just described to you, combine it with a local model of fermions with a physical fermion, which I'm going to call C, and condense the bound state of the emergent fermion with the physical fermion, and produce out a fermionic topological phase, which inherits a lot of its properties from the bosonic shadow that we started with originally. So this procedure looks schematically like the following. So the path integral of the total theory, which is going to depend on a manifold, a gauge field for the bosonic part of the symmetry group, and a spin connection or a generalized spin connection in our case, spin structure or generalized spin structure in our case. And what we're going to do is take the bosonic shadow, which depends on the background gauge field, which is describing fermion Wilson lines, and add in the Guen construction, type construction for the a fermionic path integral, which has the physical fermion, and also incorporates the generalized spin structure. Now, condensing the fermion means gauging an anomalous D-2 form symmetry of the shadow. Really, that's where we're going to be summing over the background gauge field configurations here. Now, the construction as it is discussed in these papers requires the symmetry group to be a direct product of fermion parity and a bosonic symmetry group. and depends on a spin structure. And we generalize this to a more general symmetry group. And this depends on an object called a GF, which we call a GF structure, which looks something like this. I don't have the time to go into this in any further detail. One of the technical things that we did in our paper is very carefully account for anomalies in this fermion condensation procedure. I don't really have the time to go into that at the moment, but I would like to mention that there's a particular special case that we're able to do, which is with when time reversal squared is -1 is fermion parity. So it's a known result that if I give you a 3+1 dimensional SPT in this symmetry class, the path integral on the manifold RP4 with a fixed pin plus structure is an anomaly indicator. And the fermion SPT classification is Z16. And we're actually able to explicitly evaluate our path integral in this particular case. And it depends on a bunch of data, like topological spins of the anyons, and something that we can define precisely, but intuitively, it corresponds to the local eigenvalue of t squared acting on a particular anion. But I bring up this example in particular for a mathematical reason, which is that for a particular input category with time reversal symmetry, which is this SO3 level 3 supermodular category, we find that we get a nu equals 3 element of that our construction produces an SPT, which is the nu equals 3 element of the Z16 classification in the symmetry class. And the mathematical interest here is that RP4 has a cousin called Q4, or fake RP4, which is homeomorphic but not diffeomorphic. So that they're continuously equivalent but not smoothly equivalent. These are known to be these two manifolds are known to be distinguished by this particular Bordism invariant. And these two cousins this is an exotic structure, or sorry, exotic smooth structure on this manifold, and our path integral is able to detect this exotic smooth structure. So with that, I'm out of time. So let me just leave up the conclusions, which is that given a fermionic SET, we can produce a model for a fermionic SPT, which hosts the SET and its surface. Thank you very much.
All right, great. Thanks, Denny. Let's see.